So we have finished all the individual details of this section, meaning we've finished all the individual things of finding increasing and decreasing, and we've finished all the individual things of the relative extrema. But what we want to do now is we want to combine this information with what we did at the very beginning part of this class. In Chapter 1, we focused on graphing. For reference, let's go ahead and look back. We focused on, first, graphing polynomials, which the steps are outlined here. We found some points. The easiest points to find were the x-intercepts and the y-intercepts. We looked at the end behavior, meaning what's happening on the very left and very right-hand side of the graph. We looked at what's happening in between our x-intercepts to fill in all the missing pieces, meaning by multiplicities, whether it would cross the x-axis or bounce back the direction it came from. And then we plotted extra ordered pairs if we felt necessary. We plotted all of that on the graph, and then we checked with the graphing calculator. That's how we did it if we were trying to graph polynomial functions. Let's see how we did it if we were trying to graph rational functions or fractions. Basically the same steps, but tweaked a little bit. We plotted the points, meaning the y-intercepts, the x-intercepts. We found the asymptotes by determining what values were excluded from the domain when our denominator was equal to 0. We looked at the end behavior just like we did in polynomials, meaning what's happening on the very ends of the graph. When we just had college algebra information, we used the face case. Now that we have calculus information, we will use limits. Limit as x is approaching infinity and x is approaching negative infinity. We plotted all of that information on the graph. We plotted extra points to fill in any missing details, and then we checked with the calculator. Now these are two different sets of steps for both polynomials and rational functions, so we want to kind of condense this into one set of steps. But not only that, we don't want to have to fill in the missing pieces with just plotting extra points. There should be a better way to fill in those missing details. And that doesn't matter whether we're looking at rational functions or whether we're looking at polynomials. Plot more points if needed. We want to have a better way to fill in the missing pieces. Well, that better way is now what we've just learned in this section, what we've learned in calculus. So let's combine all these steps and combine them with the calculus information that we just learned. Steps to graphing all functions. Number 1, we find what values are excluded from the domain, meaning if there's a denominator, what makes that denominator 0? Because that gives us the vertical asymptotes. If we have square roots, we know that we can't take square roots of negative numbers. Those numbers just don't apply on our graph. Then we find the end behavior, and we do that by using calculus information, the limit as x is approaching positive infinity, the right-hand side of our graph, and x is approaching negative infinity, the left-hand side of the graph. So if you need to go back and review infinite limits, this would be a great time to do so. We plot the same points that we did back in Chapter 1 with the college algebra information. Our y-intercepts by plugging 0 into the function, and our x-intercepts by setting our function equal to 0. And now, instead of just plotting points to fill in the missing details, now we get to use information that we've just learned. We get to plot all maximums and minimums, and in between those maximums and minimums, we need to show where our graph is increasing and decreasing. And of course, we do that by setting our derivative equal to 0. Now, there still may be times where that's not enough information for you, and so we still may have to fill in any missing details, but this should be minimized compared to what we did back into the college algebra portion of this class. Of course, we plot all that information on the graph, and then we double check this with the graphing calculator. Now, these are the steps that I would tell you because I'm the teacher, but if I was a student, I would maybe rearrange these in just a little bit different order. I would probably do my graphing calculator first. That way, if I'm running through my steps and I see that something's not matching up, I can double check that individual step as I'm going along the way. Rather than me working through all the steps, seeing that I've made mistakes on all the steps, and then when I check it with my graphing calculator, I see that nothing matches up, and I have to completely redo the whole problem. So maybe if you're sitting at home doing this, I would encourage you to graph this first and double check every step as you're going through. Okay, so now that we know what the steps are, let's see how to use these in an actual example. So I have capital F of x here is equal to 3x squared plus 11x minus 4 all over x squared minus 5x minus 6. And I have the same steps outlined here. Step number 1, find the domain. 2, in behavior. 3, y-intercept. 4, x-intercepts. 5, find out where our graph is increasing, decreasing in the relative extrema, meaning maximums and minimums. And then plot all of that information on the graph and double check it with your graphing calculator. So this would be the perfect time for you to pause the video and walk through all of these steps on your own. Okay, the very first thing that we need to do is find the domain. We know we do that by figuring out where square roots of negative numbers are. That does not apply here because I don't have any square roots in my problem, and where our denominator is equal to 0. So what I need to do is I need to set my denominator equal to 0. This factors as x minus 6, x plus 1, because that multiplies to give me a negative 6 and adds to give me a negative 5. So when I set each of those equal to 0, that gives me x is equal to 6 and x is equal to negative 1. So those are the values that are excluded from my domain, specifically when our denominator is equal to 0. Therefore, that gives us the vertical asymptotes on the graph. Okay, the end behavior. We need to find this by taking the limit as x is approaching both the positive and negative infinity of my function. Now, since this is a rational function, we could double check this by using our face case things that we learned back in the college algebra portion, but we might as well go ahead and use the calculus limits rules that we've learned. We know that we want to divide everything by the highest power of x in the denominator, so I need to divide every single term by x squared. Okay, so now I can simplify this. And so I can cancel out some of these x's. And so that leaves me with 3 plus 11 over x minus 4 over x squared over 1 minus 5 over x minus 6 over x squared. So when I'm looking for the limit of this as x is approaching infinity, remember anytime I had a constant over x to some power, the denominator grows quite fast, but the numerator stays constant, and so all of these are actually going to approach 0, and that is when I plug infinity in for them. So all of those become 0, so all I have to worry about then is this here. Well, 3 divided by 1 just simplifies to be 3. So my end behavior of this graph means at 3, I have a horizontal asymptote when y is equal to 3. So on the very left and the very right-hand side of the graph, doesn't matter whether I plug in positive or negative infinity, this is going to happen. I have a horizontal asymptote there, and my graph is going to follow that horizontal asymptote on both ends. To find the y-intercept, I just find f of 0. That leaves me with the constant terms in both the numerator and the denominator. So if I simplify this and put it in ordered pair form, that gives me 0 2/3. For my x-intercepts, I set my whole function equal to 0, but I know that I can do my magic trick to cancel out the denominator. So really, I just need to set my numerator equal to 0. And I can do this by factoring. The outside gives me a positive 12. The inside gives me a negative 1. So that gives me x is equal to 1/3 and x is equal to negative 4. And so that gives me points or ordered pairs at 1/3 0 and at negative 4 0. Now, in the college algebra portion of this class, this is where we would end, and hopefully this would be enough information to give us what the graph is doing. Now, there's a lot of missing details here that we need to fill in, and so that's why we move on to the calculus portion of the class. And we try and figure out where this graph is increasing, decreasing, maximum, and minimum. Because of time, this is where I'm going to stop this video, but in the next video, we'll come right back to this, where the graph is increasing, decreasing, maximum, and minimum by using the derivative and calculus.